And we pass to the other speaker of the session, who is Paolo Malgaretti from Helmholtz Institute in Langen, Nuremberg, and is going to give a talk on transport and electrolytic across various section channels. Please, Paolo. Okay, thank you.
So, hello everybody. I hope you can hear me and you can see me.
We can see.
Yeah. Good. Okay. I would like to thank the organizer for giving me the chance, and I'm very sorry I could not take the chance to come from the workshop as a next edition in the near future, to have the chance to come and to take part personally in this very interesting scenario, and also with this set of topics. So today we'll talk about electric transport across section channels, and the title is already telling you that I'm a bit stepping away from the topic of ion channels. So what's the reason? So one of the first reasons is that ion channels typically, as we've seen in these talks in the last 2 days, typically are relatively narrow, angstrom, several angstrom, a few nanometers, where the molecular nature of physics, whereas the perspective I would like to have is a bit more coarse-grained, and therefore it naturally goes into the realm of continuum models, and continuum models are more reliable when we go to larger structures. So we try to move from ion channels to pores, where the section of this varying section channel or pore can be some nanometers, several nanometers, or if you want, even several micrometers. And somehow we are making a link, or I will try to make a link between the problem of the ion channels and the problem of the pores, and this link automatically put in contact the problem of ion channel to a set of problems that are very interesting also in other fields. For example, we have clearly the problem of micro and nanofluidics, and this can be clearly connected to the problem of energy harvesting. Then the problem of transport of electrolytes across porous materials or pores and channels is also connected to sensors. When you want to sense something, you may get a current out of it, or soft robotics, because in many cases you have some hydrogels and you have charges moving around, and therefore it's important to know the physics and the dynamics of these charges, possibly to optimize the transport and therefore the motion of these soft robots. And also is very important in what today is called continuous flow chemistry, in which people in practice try to have chemical reactions in micro and nanofluidics devices, and then again you can try to control this chemical reaction, for example, by controlling the properties of the wall. So first of all, I hope to have make clear that we are going to step microscopic, and this is kind of broadening our perspective. So this seems that we're losing something, but I hope that you see slides I will show you from the perspective of ion channels. So this fact of widening the scenario also allow us to cast a question that what is the role of the geometry of these pores? Clearly, ion channels, membranes, microfluidic devices, they all have a shape. For example, Mauro yesterday spoke about this geometry-controlled sensitivity of a pore. But today I will bring this question in a different kind of perspective. Now, with geometry, I do not mean the section of this channel, but I really mean its shape. This is a kind of 2D perspective, and my question is, can we control the transport of electrolytes upon tuning the shape of the channel? Clearly, the obvious answer is yes. It's an obvious answer that yes, you can do it. The question is how much. The question is when a decent change of shape gives rise to a remarkable change of the flow, and when this may be disregardable. Okay, so this is the question, and again, I can tackle this question in a simple way when I look at pores and when I'm at the this is continuum theory. But the hope of this approach is that what we do understand at
Paolo.
this length scale can also, please.
Can you hear me? Sorry.
Yes.
The line is busy, is noisy. Can you switch the video off, please, just to see if we improved the audio?
What do you mean switch the video off?
Yes.
How do you switch the video off? Stop camera.
Stop camera, yes, please.
Okay. Thank you. Okay. Is it any better?
Maybe let's try this way.
Enough. Good. So the idea then is to look at the role of this the geometry and when this geometry can play a role. And I want to say in his talk that we want to something cheap and easy. So clearly one can try to do several numerical simulations of it, but this is very expensive. So what we do, we aim at reducing the 3D problem, typically axis symmetric. No? So we have our idea is that our pore is like a cylinder whose section is varying, so with axial symmetry, into a 1D problem. So the problem we have to solve is a twofold problem. We have the problem of Poisson-Boltzmann that eventually will arise into the Debye. And then we have Stokes. Clearly, this flow is slow enough and lengths are small enough that we are in the low Reynolds regime. And you see, this flux is the diffusive advective flow of ions. It is controlled by velocity and by the chemical potential. And we look at the divergence of J equals 0 means that we look at steady state. So we have some initial condition, the system goes, and then we look when the density is not changing anymore in time. So we look at steady state. And we look incompressible flow. Clearly, the physics of the problem is controlled by the boundary conditions. So it's not simply a mathematical stuff that is bothering, but really they are encoding physics. And the interesting point of this approach is that it allows you to encode different physics in the boundary conditions. You can have different boundary conditions for the wall. You can have a dielectric wall. You can have conducting wall. You can have homogeneous surface tension, homogeneous surface charge or inhomogeneous surface charge, as well as for the fluid. The last line here is telling you that you have no slip at the surface of the wall, but you can also have some slip. You can have a slip length, and you can also implement a local slip length if you want, within the same approach without any big effort as compared to what I showed you. And then once we have set up the problem, in order to put it into 1D, we do the lubrication approximation. So we say that the length of our pore is much larger than the width, such that every time we have a Laplace operator, we can take into account what's happening along the transverse direction and disregard what's along x direction. So this was a y, is a typo. So in this way, we can cast our 2D, 3D problem into a 1D problem. This is for what concerns the electrolyte. For what concerns possible additional ions suspended in or colloids suspended in, what we use is the so-called Fitzgerald's approximation. That in practice is the same philosophy. We say that we may have some colloid suspended in our fluid, and they will move because of some potential, and they will also diffuse. And this potential W is simply something that is encoding at the same time the fact that colloids cannot leave the channel. So this potential is infinite if the colloid tries to leave the channel, or is, for example, the electrostatic potential if the colloid inside the channel. And in this phi, I can also add an external electrostatic field. Okay. So now this is my local potential. Therefore, I can also define the integral of my local potential, and I will call this exponential of beta f. And the key point is that this beta f is indeed my local free energy. Okay. So this is simple. Let's say this is the Boltzmann weight, and this is the local free energy once integrated over the transverse degree of freedom. The interesting point is that if I make a factorization ansatz over my probability distribution, I simply assume that along the transverse direction, I do retain my Boltzmann weight. I can integrate my equation along the transverse direction, and I can end up in this with this 1D differential equation, where the effective potential is nothing but the local free energy. So in this way, I can really cast a 2-3D problem into 1D, and this I can solve analytically. At the end of the day, I have to compute some integrals with a computer, but I have a closed formula for all the variables, all the observables I'm interested in. So what can we do with this? Let's look first of all at a question that is also relevant for ion channels. Let's say that we have an ion that want to cross my pore. And it crosses in a passive way, it's just diffusing. Then I can measure the mean first passage time. And this is the average time that the particle, that my ion takes to cross for the first time my channel. I can measure this, and here I'm showing for you the results of the analytical model. Look at the field dots, the blue and the red. And then this is the mean first passage time, TQ. This is at the denominator, so it's 1 over it, multiplied by the mean first passage time of an uncharged ion. Okay, so when this variable is 1, it means that the crossing time equals the one of an uncharged ion. And then you see that this ratio departs significantly from 1 when kappa, that is 1 over the Debye length, matches the typical size of the channel, the typical section of the channel. So this is when the pore, if you want to use this nomenclature, is sensitive to the charge of the ions, whereas if the Debye length is too large or too short, the sensitivity becomes much, much weaker. There's always a difference, but it's not as fivefold as here, for example, for these ions. These ions, they have the same charge as the wall. Another interesting effect that you can find is that if we look again at the ratio of the mean first passage time, but now we multiply it, we always look 1 over, we compare it to the case in which the channel is flat. So the section is constant, is always constant. Then we see, that's funny, that this line clearly starts at 1. Then I do increase the corrugation of the channel by increasing this variable, that is logarithm of the maximum amplitude over the minimum amplitude. Is a way of encode the geometry of the channel. And you see that this curve has a maximum. Here you can see in the inset. So it means that I can reduce the passage time upon making my channel more corrugated. And this for me was something indeed counterintuitive, because typically what at least myself expected is that as soon as the channel is not flat, every way of transport will go down. Whereas this is saying that indeed you can even enhance it by tuning, and you can enhance for both charges of the ions. Both positively and negatively charged ions get enhanced. So this is for what concerns the transport of ions, passive transport of ions. But we can also look at what happens if we force the system. And we can force the system by different means. We can apply a pressure drop. We can apply an electrostatic field, or we can apply a chemical potential gradient, as it happens in blue energy devices, where you exploit the chemical potential difference between seawater and fresh water to extract to start work. So let's start looking at what happens if you apply a potential drop. So when you apply a potential drop and the channel is varying very smoothly, what happens is the following: that in practice, the Debye length inside the channel keeps homogeneous along the channel, and so does electroneutrality. The fluid is locally electroneutral, namely in the fluid you have as much charge as at the wall. So this means that the fluid flow I have will not fulfill incompressibility. If I look at how much flow I have in every slice, that is not the same value. Therefore, it means that the system will set up a local pressure drop to compensate, such that the overall flow is incompressible. So this means that in practice, locally, you have a plug flow due to the electrostatic forcing, and you have a local Poiseuille flow that is pushing backward, such that you fulfill incompressibility. And then the funny point is that when you put these two ingredients together, you get something like depicted here. So you have that the flow is going, let's say, from left to right, because that's the forcing, close to the wall, but in the central part of the channel, this is going backward. Okay, this is shown here. This is the velocity profile as a function of the transverse direction, normalized by the local section. And you see that when you are at the bottleneck, this orange line, indeed you have, well, a kind of, say, it's not exactly a parabolic cosinus, because the Debye length is comparable to the channel section. But then you see that when you are in the middle of the channel, you develop this non-monotonous behavior, and indeed you are flowing backward. And again, if I measure the velocity at the very center of the channel, and I measure this velocity as a function of the Debye length, we do see that when the Debye length matches the typical section of the channel, we can have this novel phenomenon. Otherwise, the velocity has the same sign as the overall flow, and if you want, is a standard scenario. So these two cases are already showing that indeed you can not only tune the transport of electrolytes across pores, but you can really induce novel phenomena and novel velocity profile by tuning at the same time the geometry of the channel and the Debye length. Now, these are numerical predictions, and one may not trust us. Therefore, we checked, indeed, in collaboration with Mauro Chinappi, and we did quite detailed molecular dynamic simulations. And indeed, we have confirmed our prediction. Yes, you have the onset of these recirculations. Now, the nice point of doing numerical simulations is that you can also explore regimes that analytical models don't allow for. And therefore, with Mauro, we force the system a bit stronger. Actually, we entered in the non-linear regime in which the currents were not linear anymore with applied voltage. And here we found something new. We found that the system, due to the drive, can break local electron neutrality. And this is what the bottom panel is showing to you. You see there are these sets of lines in different colors of blue. You have dark blue and you have light blue. This stands for different strength of the force. And you see that for dark blue, this value is about 1. That is the noise due to molecular dynamics. That is 1, so it means local electron neutrality. Well, for the light blue, you see that clearly there are regions in which the charge in the fluid is away from -1. So this means that it's not matching anymore the charge on the wall. And here you can see there's a clear minimum. And this means that you're breaking local electron neutrality. It means that you're setting up a dipolar field. And this for us was very surprising because many models assume local electron neutrality, whereas this is showing that if you push strong enough, you can break it. And then you can, for example, sorry for this. You can also set up, here is a picture of the density of ions, and you see that here in practice you have a depletion of ions. This is also captured by these yellow lines. You see that this is the density of salt, and in practice there's a region in which salt is almost depleted, and there's a region in which it is accumulated, and this is due to the flow. And again, this local electron neutrality breaking and this density polarization we do observe at most when we have that the Debye length matches the size of the bottleneck of the channel, but it doesn't in the white part. So we have that the bottleneck and the white part of the channel are in two different regimes for what concerns the Debye overlap. We can also study the same when we apply a gradient of the chemical potentials. So I'm sorry, I haven't mentioned up to now, but clearly the case of delta V was done in periodic boundary conditions. So we assume we have many channels, one next to another one. Whereas here, when we apply a chemical potential gradient, we decided to also look at what happened when we change the phase. So now I assume I have a single pore, just one, and my pore can be like depicted in the figure. It can start with a minimum, then wide, and then minimum amplitude again, or I can shift my pore of, say, pi. And then I have that at the end, my pore is widest, and the bottleneck is at the center of the pore. And then I can play with the phase shift between the shape of my channel and where I do impose my chemical potential gradient. And this is what the first panel is showing to you, showing the dimensionless transport. This chi is the dimensional transport or permeability of the channel. And again, for positive and negative ions. And then you see that upon tuning this phi, indeed, you can tune the net flow. And indeed, you can have that. You can also switch which ions will flow faster, positive or negative ions. So if both of them are there at the same time, you would switch the electric current. And the bottom panel, it is showing to you that, again, these effects, either promoting when you are above 1 or reducing when you are below 1, are magnified when the Debye length is commensurable to the channel section. So that is the regime in which you can tune the flow and the transport upon tuning the geometry. Clearly, these are two cases, separate cases, but one can also aim at, okay, fair enough. What is the Onsager matrix? Let's say now I can identify my fluxes. I have JQ, that is the electric current. I have capital Q, that is my volumetric fluid flow of the solution. And I have my JC prime, that is the flow of the solute on the top of the flow of the solvent. And if I choose these fluxes, and if I choose as independent forces the electrostatic field drop, the chemical potential drop of the salt, and the pressure drop, then my Onsager matrix is symmetric. So my coefficients are symmetric, and for example, L13 is equal L31. Okay, and these zeros that you see here indeed are because of the Debye approximation. If you would go beyond the Debye, then these matrix elements would not be zero anymore, but they would be finite. Now, the interesting point of having the Onsager matrix is that once you have the coefficients, you can ask yourself every kind of question. You can ask yourself what happens when I apply a delta V and a delta mu at the same time, such that one of the fluxes is zero or not. So you can really play around and see what happens in the different scenarios. And again, one stuff that for us was a bit surprising is that we start measuring the flow, in particular, in this case, the electric current, as a function of the geometry, again, encoded in this variable, delta S. And we normalized by the case in which delta S is zero, again, the flat channel. The interesting point is that while the diagonal elements, typically they go down with delta S, so namely the maximum electric current that you have if you apply a delta V is when the channel is, its section is homogeneous. Some of diagonal terms, in particular L12 and L21, because they are the same, they show this behavior that is very interesting. So you see that the flow, so the current, the electric current that you have upon applying a delta mu grows with delta S. So the key point is that the more corrugated is the channel, the higher is the current. And this happens for the electric walls, whereas for conducting walls, these may depend on the Debye length. You can have some, for conducting walls, you can have some geometries for which you increase with delta S and then eventually you go down, whereas for the electric walls, this current will grow with the corrugation. And the rationale of it is that when the channel becomes more and more corrugated, some ions find very hard to go through, whereas some other ions find it very easy. And those that find very easy are the co-ions from the perspective of the wall. So those ions are attracted towards the wall, whereas those ions that have the same charge of the wall, sorry, the co-ions, not the counter ions. So the ions that have the same charge of the wall, for them it's hard to go through the bottleneck, and that's why you increase the electric current when you tune the geometry. So with this, I conclude this brief review about what you can do with a pore. And the message I want to convey at the end is that this that has been shown in the case of continuum theory, it is likely to hold also when you go down. The problem is that when you go down to the ion channels, where you have a fewer molecules involved, the problem is that it's not so easy to write down these effective and local free energies. And that's why this model at the moment cannot be applied there. But if we have access to the local free energy, then indeed we can use it to really see what happens upon tuning the diverse parameters. So before really concluding, I want to acknowledge people I've been working with. The majority of this work has been developed in collaboration with Ignacio Pagona-Barraga, Miguel Rubí, and with Mauro Chinappi. We have done this work on the numerical simulations. And to conclude, just to recap, I've shown you that geometry can control different kind of transport. We can control diffusion. You can have ionic flow when you apply a chemical potential gradient. We can control electrosmotic flow and also other cross transport coefficient. And the key parameter for electrolytes is...
Ci sono domande?
Sorry?
Sorry.
Is the Debye length lambda, and the key point is that Debye length lambda should be comparable to the minimum size of the channel and smaller than the maximum amplitude of the channel. So with this, I'm done. Thank you very much for your attention.
Okay, thank you very much, Paolo, for this nice talk. And so I try to see if there are questions on the chat. For the moment, not yet. But I had problem with the chat, so the updating of the chat. I can ask you a question if you don't mind. Mm-hmm. One of the hypotheses for your theory, the Fick-Jacobs approximation, is the homogeneity of the distribution of particles in the vertical direction, the homogenization, let's say, in the vertical direction. But when you work with charged particles, these hypotheses can be strongly violated.
Yes,
can you say something
actually,
about?
Yes. Partially is my fault because here there was an equation somehow did not appear. I'm not assuming that. I'm sorry for that. Let me rephrase better. What I do assume is that my P xy factorized in a row times E minus beta W. Yeah. And this means E minus electrostatic potential. So I'm not assuming that my ions are homogeneous along the transverse direction. I am assuming that they are distributed as at equilibrium.
As at equilibrium, so.
Even though then I apply an external force along the axis of the channel and I have a transport. So in this sense, it's an approximation, because if you push very, very strongly, they will not retain their equilibrium distribution along the transverse direction. But there's no, one of the key points, there's no homogenization here.
Okay.
Thank you for the
question.
But
anyway, there is the need to reach the equilibrium along that direction.
Yes.
That is not granted, it's not assured for a general problem, or not?
No. It's an approximation. So word approximation means it is wrong. The key point that this is right, or let's say the approximation is reliable when the channel is varying smoothly and when the external force is not so strong. So this is linear. Within linear response, in practice, this is fine.
This is fine. Okay, for the moment, there are no questions, but I have just about the corrugation. You said that you can push your theory till to strong corrugation. How much how much is the corrugation that you support with your theory?
Oh, concerning corrugation, there's no trouble. You can, in practice, go up to closing the channel. The problem is that if it becomes too small, then continuum theory is not reliable anymore. Here, the big problem is is really the length of the pore versus the width of the pore. Provided that the pore is going down gently, so that H over L is much smaller than 1, then the theory will work. Also for very narrow constrictions.
Okay, so there is no restriction for the corrugation?
No, in this sense, no.
The derivative of the corrugation, no, okay.
No, exactly. Provided that the free energy use is reliable.
Is reliable. Okay. Okay, let me check the chat. No, it seems that there are no other questions, so I would like to thank you for this nice talk.